Hi everyone, today we're going to continue on with elimination reactions. So we're going to look at substitution versus elimination, and we're going to look at all the factors that affect both substitution and elimination reactions. So when we talk about the strength of the base, remember that for a E2 or SN2 reaction, we have to have a strong nucleophile, which is typically or is a strong base. So something like OH is a good example, any OR group. We have ionic salts, so something like sodium chloride would give us Na+, Cl-. So those are all going to be considered strong nucleophiles. When we have a weaker base, so SN1, E1 reactions will proceed with a weaker base or weaker nucleophile. So remember that because the carbocation formation is the rate determining step, the concentration of the nucleophile does not affect the overall rate of the reaction. So this is why weaker bases or nucleophiles work for SN1 and or E1 reactions. So weaker bases would be something like water is common, alcohol is common, acetic acid is another one that you guys may see. So when we look at our the steric bulk, so steric interactions or steric hindrance, so when we have a SN2 reaction or a E2 reaction, the more steric bulk we have, it's going to favor E2. So this makes sense if you think about it, because remember for SN2 reactions, we have inversion of our stereochemistry, so we have that backside attack. So if we have a lot of steric interactions or steric hindrance with our substrate, it's going to be really hard for that nucleophile to go in for that backside attack. So again, if we have a strong base in the reaction, but our substrate is really bulky, then it's probably going to favor E2 versus SN2. The same thing for if we have a bulky base. So we talked about this tert butoxide. So this base right here is typical. It's going to favor typically E2 reactions unless it's on a primary substrate. Then SN2 products will also form. Let's look at our general reactivity versus the halide type. So if we look at a methyl halide, so a methyl halide is going to be CH3X. So the only reaction that this is actually going to undergo is going to be an SN2 reaction. So again, only proceed via SN2 reaction. When we look at primary halide, so a primary halide is going to be something like RX. So primary halides are going to generally favor SN2. And then E2 would be favored if the base is bulky, or there's some sterically hindered substrates. So the reason that SN1 reactions and or E1 reactions will occur, so they will occur on a primary halide if we have an allylic or benzylic halide. So remember, the reason for this is because these, both allylic and benzylic, can produce resonance stabilized carbocations. So remember, after the first step, that the carbocation intermediate is what is formed. So if we can stabilize that carbocation by resonance, then, and we have a weak base or weak nucleophile, it will proceed via SN1 E1 reaction. Another way or reason that a primary halide will proceed via SN1 E1 would be if the substrate can rearrange. So remember, we have hydride shifts, we have alkyl shifts. So remember, hydride shifts are shown like this. Alkyl shifts are the movement of an R group, like a methyl group, for example. So if we can move this, the substrate can rearrange to a more stable carbocation, which is concurrent with the ionization, then the reaction will proceed via SN1E1. Again, we have to think about a lot of other factors too. We have to look at the base. So if our nucleophile or base is a weak base and it's on a primary, think about things. How can I stabilize this? Because a primary carbocation is very unstable, so a SN1E1 reaction cannot proceed via a primary substrate. But if we have an allylic or a benzylic or a hydride shift or alkyl shift, that's kind of the way you want to start thinking. When we have a secondary halide, so two R groups coming off of the substrate. So really all of the reactions are possible when we have a secondary halide. So we're going to have a lot of different factors that we have to think about, right? We have solvent. So remember that E2-SN2 reactions will use polar aprotic solvents, where when we have SN1 reactions, E1, typically it's going to be polar protic solvents. So solvents are going to play into that, and then the base or the nucleophile is also going to favor a specific outcome. So if we have a strong base or nucleophile, it would go SN2E2. If we have a weak base or nucleophile, it would go SN1E1. If we do have a bulky base, but it's strong, then it's going to, again, favor that E2 because it's going to have a hard time doing that backside attack for an SN2 reaction. Because remember, they are only one-step reactions. If we look at tertiary, so tertiary, the strong base, so if we have a strong base for a tertiary, it will only favor E2. So tertiary cannot undergo SN2. So since they can't undergo SN2, if you have either a bulky base, a strong bulky base, or even just a strong nucleophile in general, it's going to proceed E2. If we have a weak base or a weak nucleophile, then again, it's going to favor that SN1E1 reaction. So solvents, I did just mention solvents, but when we look at solvents, we have, remember, polar aprotic. So remember, polar aprotic aren't capable of forming hydrogen bonds. So that's going to be favored for SN2E2 reactions. We have polar protic. So polar protic do form hydrogen bonds, so something like water, alcohol. So this is going to be SN1E1 reaction. Something else so that we haven't really talked about, so concentration. So if all four reactions are possible, the higher concentration of the base or nucleophile will generally favor SN2E2 over SN1 or E1. So again, it can be concentration dependent. And then the same thing with temperature. So these reactions can be temperature dependent. So higher temperatures will typically favor elimination over substitution. So if we have, for example, two products formed, but the reaction was heated to higher temperatures, it will probably favor the elimination reaction over that substitution. So we may have some of the substitution product present. It would just be more of the elimination product would be present in the reaction mixture. Another thing that I should mention is going to be sulfuric acid. So I'll do an example with sulfuric acid, but when you see sulfuric acid and heat, so it's going to be shown like this will proceed via only E1 reaction only. So we'll look at the last example that we look at today will be one with sulfuric acid and heat, and I will show you how that mechanism works. But again, sulfuric acid and heat is only going to proceed E1. All right, so let's look at some different examples. So first example we're going to look at is going to be this right here. So what we have is, that should be bromine. So we have a tertiary, we have an alcohol, right? So this is going to be weak. We have heat, so this is going to tell us that elimination is going to be favored over substitution, but we know that this is going to proceed SN1 and E1. So if you were asked just to draw the products, which is kind of what you've seen in lab, this would be your SN1 product, and then we would have your E1 product. So again, remember your E1 product is just beta elimination, so you're removing that hydrogen from a beta carbon. If we look at another example, so let's look at something like this. So this is going to be ionic, right? So we have minus here, plus here. So we know that this is going to be a strong nucleophile or strong base. So this is a primary carbon. So what would happen is our two products would be our SN2 product, plus we would have our E2 product. So again, we have our alpha here, beta. So E2 product is going to be a one-step product, and it's coming from the removal of a beta hydrogen. Now, what if we change that base? What if we have something like this substrate, which again, same thing on a primary, and we have that tert butoxide. So remember, tert butoxide looks like this. So we want to think, okay, this is strong, but this is bulky. So what's going to happen is now, so say the reaction above this was 90% SN2 and it's 10% E2, for example. When we look at this reaction here with the bulky base, what's going to happen is we can still form our SN2 product because this is on a primary halide. But now we would only have like 15% of SN2, and these of course are all approximate, and we would have 85% of our E2 product. Again, the only reason that this can even proceed via SN2 is just because this is a primary halide as our substrate. All right, let's look at another example. So if we look at this reaction right here, and the reaction is done in DMF. And this is our nucleophile. So again, this is going to be ionic. So it's OR minus and sodium plus. So I would hope that you guys are thinking, okay, this is going to be SN2 and or E2. So if it is SN2, there's something that we have to think about. We have to think about stereochemistry because this is a stereocenter. So remember, we are going to have inversion. So since we have inversion, our product would look like this, so backside attack. And then we would also have our E2 products. So E2 is going to be, again, beta elimination. So the only hydrogen we can remove would be from this beta carbon right here. So this would be our E2 product. This would be our SN2 product. So if you're thinking about this, one of these is going to be major. The one that's going to be major is going to be this E2. And the reason that this is major and the SN2 is minor in this case is because of this reaction right here is going to be slower due to sterics. So the steric, right, we have this kind of group right here, which is going to build some steric interactions, which is going to make it harder for that backside attack. Let's look at another example. So if we have, so same substrate, this time we're going to use an alcohol. So alcohol, again, is going to be a weak nucleophile or base. So we're on a secondary, so we know it's going to precede SN1E1. So we have the formation of our carbocation as our first step. So every time you have an SN1E1 reaction, again, you want to think allylic, benzylic. So is there a way I can use resonance to stabilize this carbocation, which in this case we don't have that? Or is there a way to have a hydride shift or an alkyl shift to move the carbocation from a secondary, in this case, to a tertiary? So we can do that. We can have an alkyl shift, so the movement of a methyl group. So when we do that, we're moving, say, this methyl group right here. We're going to move that to the carbocation. So now we're putting our carbocation, we're stabilizing it more, we're putting it on a tertiary carbon. So now we can, there's a lot of different products that we can form. So let's think about our substitution products first. So SN1 products. So we have both retention and inversion. This is a stereocenter. So we have this product that can form. We have this product that can form. Now, if we think about our carbocation that is on our tertiary, we're also going to have this product that can form, plus we have this product that can form. So again, we have to show all stereochemistry, so we have to show retention and inversion products for SN1 if that carbon is a stereocenter, which in this case it is. So those are all of our SN1 products. So now let's think about our elimination products, so our E1 products. So again, I'll draw that. So we have, I'll draw this down here for you guys so it's a little bit easier to follow. So again, we have that alkyl shift. Now we're putting our carbocation on a tertiary carbon. So now our elimination products. So we have to think about all our, right? So we have an alpha here. So this would be a beta. This would be a beta, which we don't have any hydrogens in that position. Same thing here. We have an an alpha here. So this would be our beta here, beta here, beta here. So there's a lot of different products that can form for elimination also. So we have this product here coming from this intermediate here. We also have this product here is a possibility. We have this product here. So this is our cis. We also can form the trans. And then we also have this product here. So again, there's a lot of products that can form. I think the easiest thing to do when you're approaching an SN1 or an E1 reaction, again, think of allylic, benzylic, think of hydride shift, think of alkyl shift. But after you think about all of those, just draw the intermediates first, and then that will help you to draw all the products. So if you're just asked to draw the products, you would do exactly as I'm doing right now. If you're asked to draw the mechanism, then you'll have to show, again, the flow of electrons with using arrows to show each step. Now let me show you one more example. So we haven't really talked about this. So this is the example with sulfuric acid and heat. So whenever you see this, it's going to precede E1 only. So let's look at this example right here. So we have a tertiary carbon. So our substrate is tertiary. We have a poor leaving group. So OH is a strong base. That's going to be a really bad leaving group. So what actually happens, this is why sulfuric acid works. So the sulfuric acid is going to protonate that OH. So what we're going to be left with is this substrate here, which again, if you can make a bad leaving group a good leaving group, if you have a reaction and you have a substrate and you're like, okay, that's a bad leaving group, think of a way, is there a way that I can make it a good leaving group? If there is a way that you can make it a good leaving group by protonating it, then that is the approach you want to take with whether it's sulfuric acid, or we looked at another example in a prior lecture with like hydrochloric acid. So now that we have this H2O, what happens is this is a good leaving group now. So we can form our carbocation. We have the formation of our carbocation. So after the formation of our carbocation, we have to think, okay, this is our alpha. We have beta, beta, beta. So really all of the products are going to be the same. And what happens is that water is going to act as a weak base. And this is going to help to eliminate that proton. And we will be left with the formation of our product. So again, there are more complicated substrates that you may see, but whenever you see sulfuric acid and heat, I want you guys to think, okay, this is going to proceed via an E1 reaction only. So practice, practice, practice. Work on all of the problems that I am giving you. Work on Professor Rosenstein's, work on Professor Madrick's. And if you have any questions, please reach out to me. You will be expected to draw the substitution and elimination reactions. So when we started with substitution reactions, I did mention that sometimes these aren't the most ideal reactions, and I hope at this point you can see why, just because there are so many products that will be in solution. So sometimes it makes it hard for purification or separation, depending on what your target species is. So again, please practice, reach out to me with any questions, and I hope you all are doing really well. I miss having our in-class lectures, but I will hopefully see you all over Zoom soon. Have a great day, everyone.